Okay, so now a bit of a different direction from our one sample inference. Now we are still going to talk about one sample, but now this one sample is referring to the differences of our observations. Now, thinking back to Unit 3 when we were doing data collection, we learned about a specific type of experimental design called matched pairs design, in which one of the following situations is used. Essentially, it's blocking with size blocks of 2. And we have the few options here. So for example, perhaps your data is paired with 2 separate individuals. So they are either matched as similarly as possible, perhaps they're spouses, twins, siblings. They are just essentially this as similar as possibly can be so that we can reduce the variation. Or data is paired within the same experimental unit, meaning before and after study, or perhaps one experimental unit receives 2 types of treatment. Now, here's a few key concepts that we need for this section, but we are going to be looking at comparative studies, meaning there's either 2 observations on one individual or 1 observation on 2 separate individuals. Now, comparative studies tend to be more convincing than single sample, as one sample inference tends to be less common than comparative inference. And when you think about it, it is a lot easier. It might, in theory, seem easier to find just one group of people, take the sample from there, but at least looking at a comparative study, since we're measuring that same person or same subject or item, we are able to see the differences in the trends between the 2 treatments. So we can see how that one person would respond to the 2 treatments, as opposed to a completely randomized design where maybe if we haven't blocked properly or addressed confounding variables, maybe our results are all over the place and we're not quite sure how to fix that variation there. Now, by measuring the same explanatory variable twice, we can make comparisons by analyzing the responses in each pair. Again, this just means either the same person receiving 2 treatments or 2 separate people receiving the same treatment. And we analyze pair data by first taking the differences within each pair to produce a single sample. Then we proceed to use one sample T procedures. So whether it's one person receiving 2 or 2 people receiving 1, what we're going to do is we're going to take the difference between those pairs, and that'll give me unique values of the differences. So here we're looking at the average difference of the paired data. Now, thankfully, because it follows one sample procedures, we are going to still be able to use our models that we've learned from the previous lessons, including the panic model and phantoms. So here, the parameter is mu d instead of just mu, which is the true population average difference of. Our assumptions are that it's stated random, the data is paired, it's independent using either 10% condition if we're sampling without replacement, or assuming that the results do not influence another, and normal by one of these 3 conditions or criteria. Now, the data is paired isn't an official AP exam condition. In fact, it's more of a recognition. So I'm actually going to show you how you would do condition 2 and then this second bullet point on condition 3 together. Now, the official name can be either or. If the conditions are met, you can use a matched paired t interval, matched pairs t interval for a mean difference, or you can use a paired t interval or paired t test. So as long as there's the p word, the pair in there, then we should be pretty good. Interval calculations, very similar to our one sample inference for mean. Notice now, though, that this is xd, which is the mean of the differences, and this is sd, which is the standard deviation of the differences. And then degrees of freedom is still n minus 1, and then, of course, we are C% confident that the interval from blank to blank captures the true parameter. Okay, so let us go ahead and try it out. A sociologist wants to investigate the ages of grandparents of high school students. From a random sample of 10 high school students, the sociologist collected data on the current ages in years of the students' maternal grandparents, and the data is shown below. So here is student A through J. We know we have 10 observations. We can see that here is the first grandparent or the grandmother, and then we have the average and the standard deviation of grandma. Then we have the age of grandpa, and then we have the mean and standard deviation there. Now, these data sets, each student is independent, A, B, C, D, E, but notice that here in the pairs, the difference will depend on the pairs, and specifically in which way we choose to subtract the pairs. So if it's not given to you, so here we have the math, right? So I can see 75 minus 74 is 1, 70 minus 75. So if it's not given to you, normally we'll just go top to bottom. But as you can see here, we have this separate row for the differences. And so I'm only going to be using this bottom row. And so while it's helpful to have the rest of the information, it's not necessarily as vital because they just could have given me the mean and the standard deviation of the differences, and I would still be able to proceed with our inference procedure. So let's go ahead now. Let's try and do the parameter, the assumptions, and the name of the test, and then we'll go over the interval and the conclusion together. Now, since it didn't tell us anything about normality and our sample size is not officially large, you are actually going to have to plot these differences to see if it's unimodal and symmetric or if there appears to be no extreme skew or outliers in the data set. So I'm going to leave this here for you. Go ahead and take a few minutes, pause the video, and try and name the procedure, check your assumptions, and list your parameter, and then we'll come back and finish out the interval together. Okay, so hopefully you were able to at least get through the parameter, the name, and the assumptions, and whether you chose the histogram, dot plot, stem plot, or box plot. I don't know which one I didn't say. Hopefully it looks relatively similar to this. My rule of thumb is dot plots are just better to assess the shape for smaller samples because in a box plot we can't see the official shape. We can only see symmetry, right skew, or left skew. So my rule of thumb is if it's like 10 or 12, dot plot it. If we are doing comparative and it's a lot, meaning more than 12 or 15, then I would suggest the box plots. But this was a small enough data set, only 10 data points, where this was a quick sketch. And I can see here this appears bimodal, but if I were to do a box plot or a histogram, or just a box plot actually, I would be able to see it would just look symmetric. So here I can see a little bit more information about my data, but for the most part this data looks approximately symmetric, and it doesn't appear that there's any extreme skew or outliers. So it looks like here my mean happens at negative 1.8, 4 observations above, 6 observations below, but again this is no extreme skew or outliers that we'd have to worry about in our procedure. So let's go ahead and construct and interpret a 95% confidence interval for the population mean difference in age of the maternal grandparents of high school students. And again, since it was provided to us, we don't have to worry too much about setting it up ourselves, but if it didn't provide it to us, we would have to define the subtraction order. Well, here, mu d is going to be the true population mean difference of age of maternal grandparents. Now, we have a few assumptions that we must check. And we see here that we used a random sample of 10 high school students. And since each pair of students belongs to one student and separate students are being sampled, we can assume the results of age differences are independent. And we can assume that the 10 high school students we sampled from is less than or equal to 10% of all high school students. We were not given any other information as to the population of interest, so we're just going to assume it's all high school students. And then we saw that our sample data shows no extreme skewness or outliers. That is one of our 3 criteria, so the normal model is appropriate. So notice that before our assumptions were stated random, independent, and normality, and here we still have that, just conditions 2 and 3. We still use the sampling without replacement to the 10% rule, and then now we're just adding that extra sentence of why they are independent. So before, in one sample inference, sampling less than the 10% ensured that the degree of dependence was negligible between observations, but now since the data is paired and each pair is being measured separately, we can also assume those results are independent. Now, since our conditions are met, we'll use a matched pairs t-interval for a mean difference. Now, here I know that the degrees of freedom at 10 observations minus 1 gives me 9. I use the summary statistics provided to me of negative 1.8, 5.81 over the square root of 10. And of course, this t-star value comes from our handy-dandy t-table. I have 9 degrees of freedom, and at 95% confidence, the critical value is 2.262. Now, if you do it by hand, you would obtain a very close result. I did round. It was slightly different than the one provided by the calculator. This was the calculator one, but once I did the 3-digit cutoff, they were basically the same thing. So again, you just have to be consistent with your work. If you decided to just use the calculator output, you would just leave this component here as t star and then give the calculator output. And I'll make sure I do some examples that look similar to what I mean there. Now, we are 95% confident the interval from negative 5.956 to 2.356 years captures the true population mean difference of age of the maternal grandparents of high school students. Now, we can see that this interval would include 0. So if it includes 0, that would mean that the differences between the pairs would be the same. That means there might not be a mean difference or an average difference between the ages of the maternal grandparents, but that's a conversation for another day. So we can see there's context, there's units, we have our confidence level mentioned, we are showing our work, we've got all the components for a full credit FRQ question. Now, I am going to, oops, that's not what I wanted to do. I'm going to move my face over. Okay. So there's an additional question here and a good thought question. One of the sociologist's research questions was about the mean difference in age without regard to which grandparent is older. The interval constructed in Part A does not address such a question, and based on the sample of high school students, give the value of the point estimate for the mean difference in age that could be used to address the sociologist's question. So if I don't care about which grandparent is older, we know a type of family function that could essentially address this negativity. Now, keep in mind that typically x bar comes to us from the sum of the observations divided by n. But here, because it's the sum of the observations, we can make this negative. It could turn out it is negative. Now, a quadratic or cubic model might not be great because that would really emphasize the difference. It would turn, the quadratic model would turn everything positive. But I don't know why I said cubic, sorry. It's because I also teach Algebra 2. Got my wires crossed. But if we just wanted to see the average difference, right, the distance perhaps from these ages, I could definitely use something like the absolute value function here and divide that by my total sample size to get the true difference here, regardless of which grandparent is older. So I'll let you plug in those numbers and try it for yourself, but if you do it correctly, you should get something like 5.2, and I'm going to need someone to check my math there. Okay, so let's see. Here's another example. This was actually the practice question on the 2020 exam, but on the 2020 exam it was a hypothesis test, and here it is a confidence interval. So let's see. Let me pause the video here in order for you to read over the question and go ahead and approach the problem, and then we'll come back and review here together. Okay, so hopefully you had an opportunity to construct your 95% confidence interval, and I really love this question because it's a little misleading at first, but a very fun question nonetheless. So mu d here would be the true mean difference of yield between genetically modified and regular corn. Now here, this is an experiment. This is not sampling without replacement, so I don't need to verify the 10% condition because our observations would be independent due to the random assignment of treatments here, and they'd be in different blocks. Well, we have the random assignment of the seeds, either genetically modified or regular, to each plot. Since each of the plots are being observed in pairs, we can assume the results are independent. And here, even though our sample data appears to have some skewness and an outlier, it is trumped over by the fact that the sample size is sufficiently large. So that hierarchy of normality conditions goes 1, 2, 3. If the population isn't normal, we check the sample size. Then if we don't meet the sample size, then we check the skewness. This is just one sample, but if I took the sampling distribution of all possible samples of size 33, I would have an approximately normal distribution. Since our conditions are met, we'll use a paired t-interval for a mean difference. Here are my calculations with the following result, and I'm 95% confident the interval from 2.251 to 6.821 bushels per acre captures the true mean difference of yields between the genetically modified and regular corn. And I got my wording a little mixed up here, sorry. But here's your last thought question for the last 20 seconds of this video. Based on their interval, is there significant evidence to claim there's not a difference? Well, if there's not a difference, 0 would be in our interval. And as we can see here, it is not. So I'll let you put that response together, but good job.